Chapter 20: Carboxylic acids and nitriles. Carboxylic acids present in many industrial processes and most biological processes. They are the starting materials to form other acyl derivatives. These include acid chloride, esters, amide, thioesters. They are abundant in nature from oxidation of aldehydes and alcohols in metabolism. An understanding of their properties and reactions is fundamental to understanding organic chemistry. The general formula for carboxylic acids is RCO2H. R is a alkyl group. One of the two oxygens is a CO double bond. The structure is R, CO double bond, and a hydroxy group. If carboxylic acids are derived from open chain alkenes, replace the terminal E by oic acid, and the carboxyl carbon atom is always number 1. For example, in the first molecule, we have 3 carbon, so it is a propane, and remove E by oic acid. The name is propanoic acid. In the second molecule, 5 carbon, so pentanoic acid, and number 1 is carboxyl carbon, and the number 4 methyl, so 4-methyl pentanoic acid. In the third molecule, 8 carbon, so it should be octane, and you have 2 carboxylic acid, so it's octane dioic acid, and number 1 carbon here, so 3-ethyl, 6-methyl octane dioic acid. Compounds with a carboxyl group bonded to a ring are named using the suffix carboxylic acid. The carboxyl carbon is not itself numbered in the system. For example, in the first molecule, a carboxyl group is connected to cyclohexane, so the name should be cyclohexane carboxylic acid. The carbon connected to carboxyl group is number 1. On number 4, there is a hydroxy group, so the name is 4-hydroxy cyclohexane carboxylic acid. Since hydroxy and the carboxyl group are trans, we add a trans on the name. In the second molecule, a carboxyl group is connected to cyclopentene, so the name should be cyclopentene carboxylic acid. Again, the carbon connected to carboxyl group is number 1, and there's a double bond, so it's 1-cyclopentene carboxylic acid. Here shows common names of some carboxylic acids. The simplest one is carboxylic acid with 1 carbon, and the name is formic acid. The next one, 2 carbon, name acetic acid, which is also vinegar that we use in our everyday life. Please go over other carboxylic acids and their names. Benzene with 1 carbon is benzoic acid. Nitriles with CN triple bond are closely related to carboxylic acids with the same oxidation level. Simple open chain nitriles are named by adding nitrile as a suffix to the alkane name with nitrile carbon number 1. For example, in this molecule, the total carbon number is 5, including the nitrile carbon. So the name is 4-methyl pentane nitrile. Since nitriles are closely related to carboxylic acids, they can also be named as derivatives of carboxylic acids. In this case, we replace oic or ic in carboxylic acid by O-nitrile. For example, in the first molecule, there are 2 carbon, and the corresponding acid is CH3COOH. The name for this carboxylic acid is acetic acid, and we replace ic by O-nitrile. so the name is acetonitrile. In the second molecule, a benzene connects one carbon. The acid is benzoic acid. We replace oic by O-nitrile, so the name is benzonitrile. In the third molecule, nitrile is directly connected to cyclohexane. The acid is called cyclohexane carboxylic acid, and here we replace carboxylic acid by carbonitrile. So the total name is 2,2-dimethyl cyclohexane carbonitrile. If a molecule already have a carboxylic acid derivative, for example, you have a ester, then the nitrile becomes a substituent. The name becomes cyanosyl group. So in this case, it should be called 4-cyanosyl, all right? And the total name is methyl 4-cyanosyl pentanoate, and this is the name for esters, which will be explained in the next chapter. Both carboxyl carbon and oxygen are sp2 hybridized. These two atoms, together with adjacent carbon and oxygen, are all in the same plane. The angles between them are around 120 degrees. Now this table lists all the angles and the bond lengths in carboxylic acids. In a carboxylic acid molecule, the hydrogen-oxygen bond is strongly polarized with hydrogen positive charge, oxygen negative charge. The positive charge hydrogen is attracted by the negative charge oxygen, and this strong interaction is called hydrogen bond. Because of this strong hydrogen bond between neighboring molecules, carboxylic acid usually has a higher boiling point than the corresponding alcohols. For example, acetic acid has boiling point 117.9 degrees. Ethanol, which also have 2 carbon, only 78.3. Since the oxygen-hydrogen bond is highly polarized, carboxylic acid can easily deprotonate this hydrogen and serve as an acid. It reacts with base, and the product is called carboxylate. Smaller carboxylic acid is soluble in water, but carboxylic acid with more than 6 carbons are slightly soluble, usually insoluble. But the product, the salt, is very soluble in water. Acid strength is measured by acidity constant, which is similar to equilibrium constant of a chemical reaction between an acid and water. The product is a hydronium ion and the corresponding carboxylate. So the acid constant is the product, which is hydronium ion carboxylate divided by the acid. The larger the Ka, the more hydronium ion it produces, the stronger the acid. Now pKa is defined as negative log Ka. So stronger acid, larger Ka, smaller pKa. This table shows acidity of some carboxylic acids, together with an alcohol and a phenol for comparison. As you already know, alcohols are very weak acid. pKa is usually around 16. Phenols are stronger, pKa around 10. Carboxylic acid are around 4.7, which is much stronger acids. Electron withdrawing group make carboxylic acid even stronger. Here we show pKa of different compounds. As you can see, hydrogen chloride is a stronger acid than any organic molecules. Among organic molecules, carboxylic acid is the strongest acid, and then phenol, and then the weakest is alcohol. As you already learned, the acid strength is determined by the stability of its conjugate base. The more stable the conjugate base, the easier for the acid to deprotonate and the stronger the acid. And we also show that phenoxide can have several resonance structures to delocalize the negative charge, stabilize the anion, compared to alkoxide. And that's why phenol is a stronger acid than alcohols. But why carboxylic acid is stronger? In other words, why this ethoxide ion is a stable ion? The stability of acetate ion is also explained by resonance structures. The two resonance forms indicates that the negative charge is delocalized between two oxygen atoms. Remember, oxygen is electron negative. So when two oxygens share the negative charge, the ion is stabilized. And if the conjugate base is stabilized, the acid is a stronger acid. Here we show 3 carboxylic acids with 2 carbon atoms, but one with a hydroxy group, one with 3 fluorine atoms. As we already shown, when acetic acid deprotonates the hydrogen, it forms acetate anion, where 2 oxygens share a negative charge. This delocalization of negative charge makes the acid a good acid. When hydroxy group is added, it will pull the negative charge away from the acetate anion through this carbon-carbon bond, carbon-oxygen bond, and this is called the inductive effect. Inductive effect make the conjugate base even more stable and make it a better acid. So pKa is 3.83. Fluorine has even higher electronegativity. 3 fluorine atoms make the conjugate base even more stable, and the pKa becomes negative 0.23. Now, inductive effect also change with distance. For example, in the last molecule, chlorine is attached to carbon adjacent to carboxyl group. The pKa is 2.86, indicates that this inductive effect is very strong. When the chlorine attached to carbon 1 atom away from carboxyl group, pKa becomes 4.05. When it is 2 atoms away, pKa 4.52, and that is very close to the acid without chlorine, and that indicates inductive effect becomes very weak when the distance becomes far away from carboxyl group. Benzoic acid has pKa 4.19. Electron withdrawing groups on the pair position can pull electron away from the conjugate base of benzoic acid, stabilize the anion, and make benzoic acid stronger with a smaller pKa. Note that electron withdrawing groups are also the deactivating group because they withdraw electron from the benzene ring, make the electrophilic substitution reaction go slow, and they are deactivators. On the other hand, the activators, methyl, methoxy, hydroxy, they donate electron to the benzene ring and make electrophilic reaction go faster, but they also make the conjugate base of benzoic acid unstable, and therefore the benzoic acid with electron donating group or activating group are weaker acid with higher pKa. Here again shows the aromatic substituent effects. Benzoic acid itself has a pKa 4.19. With electron withdrawing group or deactivator nitro group, this takes electron away from the ring but also stabilize the conjugate base and make the benzoic acid a stronger acid with a smaller pKa, 3.41. Benzoic acid with electron donating group, methoxide, or activating group, the electron becomes rich in the ring and destabilize the conjugate base, and therefore the benzoic acid becomes weaker acid, pKa increase to 4.46. Therefore, Deactivators strengthen acidity of benzoic acids because they take electron away from the system and make the conjugate base more stable. On the other hand, activators weaken acidity of benzoic acids because they donate electron to the system and destabilize the conjugate base. We can also use relative pKa to predict the effects of the substituents. For example, benzoic acid pKa is 4.19. Suppose by adding a substituent, the acid pKa becomes 5, increase, and that means it becomes less acidic. So why must be activator? Because activators weakens acidity. On the other hand, if the pKa becomes 3, that means this acid becomes stronger, and therefore why should it be a deactivator? Because deactivators strengthen acidity. Practice. The pKa of para-trifluoromethyl-benzoic acid is 3.6. Is the trifluoromethyl substituent an activating or deactivating group in electrophilic aromatic substitution reactions? So we compare this pKa with benzoic acid, and we can see the pKa becomes smaller, and that means it strengthens acidity, so the substituent must be a deactivator. Homework. Please work on problems 20.1 to 20.9 and skip 20.5.